In this lecture, we're going to go over the notes about list iterators. And before you actually watch the video, you really should read through the notes for February 24th, paying special attention to lists and iterators. Bad vector usage and DQs are important too, but we'll go over those on Thursday in class. What I'm going to go over is actually how a list is represented in memory and not so much the code, although I'll do a little bit with the code as well. So with an STL list, conceptually what you have is a set of items with a set of pointers. So maybe if it's integers, we might have something like this. And then there's a so-called start node and end node, which we call sentinel nodes. And they're not, strictly speaking, containing values in the list. They actually are part of the list, but they don't contain values. And when you see the things like list.end, what you're actually getting is a pointer to this sentinel node. Now when you say list.begin, that's a little different. With list.begin, you're actually getting a pointer to the first element of the list. So you may wonder why we have this start node. It seems to be not so useful, but remember in the notes you also had reverse iterators where you could actually go in reverse. And in that case, you would have start being the reverse end. And that is the pointer that you would get. So big point to take home is that you have a node at the front of the list called the start node, a node at the end of the list, the end node. They're sentinel nodes. They don't actually have values. The rest of the nodes in the list do have values. Okay, so with that in mind, let's actually take a look at some of the examples. And I think that the first couple examples in this lecture are fairly self-explanatory. So the one with reversing the lines in the list, that's the first example. It's simply taking a list of lines. So I'm going to just number the lines, say 1, say the lines are 1, 2, 3, 4. All that's happening is that we're inserting those lines onto a list as follows, and they're being pushed front. So the first one that's pushed on is 1, then with push front 2 gets put on next, then 3, then 4. So if we want to do it in order, we start with 1 and it's a push front, then we push 2 onto the front, then we push 3 onto the front, and then we push 4 onto the front. And so when we then iterate through the list at the end, we simply go through the list, and when we print out the lines, we print them in the order 4, 3, 2, 1. So a fairly simple one. So the next one was simply showing a different way to do list insertion. Instead of using push front, it was showing you the insert command for a list. And with the insert command, it takes 2 arguments. The first argument is a pointer to the element that you want to insert before. So it's a insert before operation. And then S is the item that you want to insert. So here, lines.begin, if you remember, points to the first element of the list, and therefore we are inserting S before the first element of the list. Now typically in this case you would use push front. It's more easy to read than this insert command, but the insert command is giving you an idea of how insert works. Now more interesting is when we insert into the middle of a list. So for example, let's say that we have a grocery list. Okay, so the grocery list, let's say we start out and let's say the groceries, well, we're a little small there, but the groceries that we have are oranges, bananas, milk, and orange juice. So oranges, bananas, milk, and OJ. And we want to insert a new element into the middle of this list. Specifically, we want to insert yogurt, and we'd like to insert it before milk. So when we're done, what we would like is for the list to now have bananas pointing to yogurt and yogurt pointing to milk. So the way that we make this happen is that, well, let's go back to our original list first. So I'm assuming that you get two arguments. One is the item you want to insert, one is the target you want to insert before, and one is your list. So if you look right here, that's what we have. New item is our new word to insert, which is yogurt. String target is the item to insert before, that's milk. And then grocery list is the list we want to insert into. So of course we have to create an iterator, which is going to allow us to iterate through the list. And we're just starting it at the first element, so that's begin. While we haven't reached that end sentinel node, we increment the iterator, and if the contents of the node to which the iterator points is equal to our target, then we're going to insert the new item at that point using this iterator. So this iterator, the insert inserts before it. So what's going to happen is initially when we say lit equals grocery list, which I'll abbreviate GL, dot begin, lit ends up pointing right here. And remember, there's a sentinel node right here that kind of means end. So lit points to here. We compare the contents of lit, which is oranges, to our target, which is milk, and it doesn't match. So we increment lit by saying lit plus plus. And that moves lit over to here, so lit now points to bananas. Again, we do our comparisons with milk and it fails, so we increment lit again. Lit now points to milk, and now we have a match. The contents of lit star, if we look at the contents of lit star, it's equal to milk, and so we are able to do our insert, and remember the insert is with lit and our new item is yogurt, and the insert is going to take place before whatever lit points to. So lit points to milk, therefore yogurt ends up being inserted right here before milk, and the STD or STL takes care of updating our pointers, so I will do it in green. So bananas now points here and yogurt now points here. It takes care of creating the node for yogurt and rearranging the pointers so that yogurt is put into the list. And we have a special case here, which is if we don't find the item in the list, then I just specify that the item should be inserted at the end of the list. So let's say, going back to this list here, that I want to insert, let's say I want to insert ice cream, and I want to insert it before cheese. Well, we can see cheese is not in that list. So when we go through oranges, bananas, yogurt, milk, OJ, eventually lit becomes equal to end. And when lit is equal to end, we fall out of our loop. You can see that right here. We keep going until either we break out, which we'll be unable to do because there's no cheese in this list, and therefore lit will never be equal to our target, which is cheese. Therefore, we'll eventually not satisfy this condition. Lit will become equal to grocerylist.end and will come out. Well, the way we can tell that our item, our target item, was not in the list is that we reached the end of the grocery list. So if our lit pointer points, or iterator points to the end node in the list, then we know that target was not found and we need to add our new item to the back of the list, which we do with pushback. And in this case, with pushback, it ends up simply putting the new item right here between OJ and the end. So what happens, I'll just erase this, it actually puts a new entry. So end is down here, creates a new item, ice cream. And OJ is made to point to ice cream, and ice cream is made to point to end. So that handles insertion into the middle of a list. The next interesting example is deleting items from the middle of a list. So obviously you might delete items from a grocery list, but the example we're going to consider here is the example of a list of integers, and we're going to want to print those lists in sorted order. So we're going to assume that we already have our list set up for us. And usually I'm going to show you this list without the Sentinel nodes because I find that they're distracting. So we have 8, 2, 1, and 10. And we want to print them out in sorted order. So what we're going to do is search through this list and find the smallest element, which you can see is 1. And we're going to print it out, and then we're going to delete it from the list, which is going to leave us with 8, 2, and 10. So again, we're going to want to print the smallest item on the list. So we search through, find it's 2, so we print it, and now we delete 2 from the list, leaving us with the list 8, 10. Again, we search for the smallest item, it's 8. We print it and delete it, leaving 10. Since 10 is the only item in the list, we of course immediately find it and delete it, leaving us with an empty list. Now, for the first time, I will show you what that actually looks like. It actually has a start node and an end node, so our 2 Sentinel nodes, but no values in between. And the list is smart enough, if we ask if it's empty, there's an empty method that we can use to ask if a list is empty. And if there's no values left, then that method will return true. So for us, the relevant function is the one that finds the smallest item in this list. So for example, out of 8, 2, 1, and 10, finds this minimum item, deletes it, and returns it. So in the code that you see here, let's actually make it a bit larger, you see that we first get 2 iterators, one called lit and one called min. So coming back to here, what we're going to do is we're going to let lit iterate through each element of the list. And then we're going to have a second iterator, min, which is going to keep track of the current minimum element in the list. Well, obviously, we can initialize min to be the first element in the list. So now we move lit through the list, and we see here that 2 is less than the current minimum, which is 8. So we update min to be equal to the current node in the list. We move lit to the right, and we see that 1 is less than min, because 1 is less than 2, so we update min to be equal to lit. And we move lit to the right. This time lit is not less than the min, so we don't do anything with min. And now we've reached the end of the loop, or the end of the list, and you can see that min has saved our place, or saved the location of the smallest item in the list. So now we can go ahead and delete this from the list and return it. So this is what the code here is doing. We set min to be the first element in the list. Then we have lit iterate through each element of the list. For each such node, we compare that node, the current node, which is pointed to by lit, and see if it's less than the minimum node. If it is, then we update min to point to the node that lit points to. And you can see we can set one iterator equal to another iterator, and that simply says I now point to the node that this old iterator pointed to. And you can also see that we can go ahead and continue to update lit, and min will not follow it. So min will stay pointing to whatever node it currently was. So when we exit the loop, we now have min pointing to the node we want to delete. We first must save the value, then we use the erase method to erase that node from the list, and finally we return the value. You may wonder, why not just call box size.erase min and then say return star min? The reason is, once we've erased min from the list, min is now going to be undefined, and there's a good chance that if right here we tried to return star min, we would get a segfault because that min node no longer exists. So it's very important that we first save the value of that min node, then erase the node, and finally return the saved value. That concludes this lecture with lists. As I said, on Thursday, we will be going into vectors in class and also into doubly ended queues. One thing you should also look at is the top coder diamond hunt example. I'm not going to go through it right now because I've already gone through 2 examples with you. But having gone through it, you should be able to now go through this code for diamond hunt, and you should be able to see how Dr. Planck has used these 2 iterators to find the diamonds in the top coder diamond hunt problem.